All right, in question 7, we're looking at a mass of 5 kilograms released from rest on a frictionless surface. So that's nice. We don't got to worry about friction. Incline at 30 degrees to the horizontal. Air resistance is also negligible. No kind of resistive forces stopping this air. Sorry about that. How far does the mass travel in a time of 0.8 seconds? So if you're dealing with masses on a incline, it's probably a good idea to resolve this and think about, well, what's the force that's going to make it sort of go down? It's going to be the component of its weight that's acting that way. So weight goes straight down, and we say we're given the mass. That's kind of a clue. We could calculate the weight mg. If this angle is 30, then that angle is 30. And so the component of the weight that is opposite that angle, right, is going to be the sine theta times mg. If that's not immediately clear, just think about your trig definitions and think about it like, here's the angle I want, there's my right angle. So the weight is the hypotenuse, right? This mg is the hypotenuse of this triangle. And then just, you know, it's easy to sort of get confused with the sine and the cosine. So you want to say, I want to know the opposite of this, because this is the component that's going to make it slide down. Remember, this vector is the same as this. I can translate this vector anywhere in space. This is a vector that points that way, right? I can say it's acting on this object here, or it's right here on this triangle that's easier to sort of see. So the sine of some angle theta is equal to the opposite over the hypotenuse. And say, okay, I want to know the opposite. I want to know that. I know the hypotenuse is my mg. So the sine of this angle theta is the side opposite, the thing I want to know. You know, we could kind of call it the component of weight in the x direction, if you will, over mg. And that's why the component of weight in the x direction is mg sine theta, right? So you just kind of get that. So that's going to be the force that makes it accelerate. And I think we can calculate all that, right? Because we know the mass, we know g, and we know the angle theta. So I think it's a good idea now to like turn this alphabet soup into numbers. Again, for the benefit of everybody here following along, we'll just do that calculation right on the screen. So we got the mass, m. We got the gravity field, g. Always use 9.81 in this course. And then we've got times let's clear all that out. So we want times sine of 30 equals. So there you go. So we have the component of weight acting down as 24.525 newtons. That's the force that's going to make it accelerate. We're trying to solve for the distance that it's going to move, right? How much is it going to go in a time of this? So if we solve for the acceleration, we could think about, you know, using an equation of motion. So if F equals ma, and we know the force is 24.525, then we can substitute that in, you know, for this. And so 24.525 F equals the mass 5 kilograms times some acceleration A. So remember, it's only a certain component of its weight that's making it accelerate. So we have to sort of figure that out first. That's the net force, right? That's making it accelerate. Only the component of its weight acting down the slope. So if we divide each side by 5 kilos, I think maybe we didn't need to, you know, the mass would have canceled anyway. Divided by 5, we get an acceleration of 4.905 meters per second squared. And then we could use an equation of motion like solving for how far, that's a displacement. So S equals UT plus 1/2 AT squared. Because we don't know like its final velocity, we could consider like another equation, you know, so what's all the equations that has displacement in it? So we have 1/2 U plus V times T. So we know the time, but we don't know the final velocity. that would require us to sort of calculate that. Well, we had to calculate acceleration to, use this one. Could we have used v squared equals u squared plus 2as? Again, we would have to have solved for the final velocity first. And so here, I think really is the path to the solution, is to solve for the acceleration and then just say, well, it started at an initial sort of rest. And so it's just going to be the displacement s equal to 1/2 at squared, right? So from rest, this term goes away. And the displacement is just going to be 1/2 4.905 times 0.8 squared, which gives you, I think, choice A. It's already done again. So just like slide that in there. Calculate that, that's going to be the future. All right, so we want, grab my erasing tool real quick, clean that up just a bit there. Point 5 times 4.905 times 0.8 squared. 1.5696 meters, 1.6 meters, choice A.